in the last class, we had seen how a three-phase supply is being generated, right? And we also came to know what is phase sequence. Okay, so if all the three coils, all the three identical coils, which are displaced 120-degree apart from each other, if they are rotating in anti-clockwise direction in a constant magnetic field, in a uniform magnetic field, then you will get ABC phase sequence. Okay, so we had fixed VA as the voltage in phase A as the reference. So in phasor form, we would get VA as V angle 0, VB as V angle minus 120, and VC as V angle minus 240. So today we are going to take up the different kinds of connections like star connection and Y connection and delta connection. Okay, star or Y connection and delta connection. Okay, let's get into the details. So star or Y connection. Star or Y connection. Okay, so we know if you have three coils or three impedances, they can be connected in two patterns. Okay, suppose there are three coils. Okay, or three impedances. They can be joined together in two ways. Okay, if this coil end, let me mark as A dash, B dash, and C dash, C dash. Okay, I can join these three endpoints to get what is called a star configuration. So suppose in a generator, the windings, the three windings A dash, B dash, and C dash, they are joined at their or at one of the endpoints A dash, B dash, C dash. Okay, then what we get is called a star connection. Okay, so this is a star configuration, right? So we are considering a balanced supply. What do you mean by balanced supply? All the coils are identical. That means they have the same number of turns. Okay, and they are rotating in a uniform magnetic field. So the voltage magnitudes will be the same, right? But the phase angle difference between any two voltages will be 120 degree. Okay, that's the meaning of a balanced or a symmetrical supply, right? Say for example, V angle 0, V angle minus 120, and V angle minus 240 if you are considering ABC phase sequence. Okay, so this is a star configuration, right? Let me mark this as A, this is B, and this is C. Okay, so this common point at which all the three phases or all the three coils meet, that is called the neutral point N. Neutral point N. Okay. So now you see this is in a generator. Generator side we have three coils. Okay. So from the generator, current is drawn. Okay. The generator has to supply the load, right? So from the generator, current has to flow to the load through lines. Okay. So these are called lines. Okay. And here we'll be having loads, three-phase load. Okay, so if this is C, this is A, this is B, then A and A will get connected, B will get connected to B, and this will go to C. Okay, so this is called a line, right? So this is line C. This is line A, and this is line B. Okay, this common point, if you want, you can take a wire from there. Okay, that is called the neutral line, right? And that can be connected if necessary with the neutral point of the load. Okay, this is called the neutral line. Okay, this is called the neutral line. Neutral line, right? Now, you can define a voltage. Okay, you can define a voltage between any one of the lines and the neutral. Say for example, between line A and the neutral line. Okay, this let me call as VAN. Okay, that means it is the voltage across line A and the neutral line. And if you carefully observe, that will be nothing but same as the voltage across the phase A and the neutral point, right? Because this is the phase A endpoint, this is the neutral point, right? So voltage between line A and neutral is same as the voltage across the phase A. Okay, phase A and the neutral. Is it not? Because they are parallel, right? Similarly, between line B and the neutral, I can have another voltage that is called VBN. Okay, or that will be the voltage appearing across the phase B. This is the phase B, right? So you are taking the voltage across the phase B. Similarly, between line C and neutral N, you can have another voltage, and that is called VCN. Okay, so this is called the phase voltage. Phase voltages. Phase voltages are also called line to neutral voltages. Line to neutral voltages. Okay, so which are the line to neutral voltages or phase voltages here? VAN, VBN, and VC. Okay, they are the respective voltages. Right? Now you see we are considering a symmetrical case. Okay, so that means voltage magnitudes are equal. VAN will be equal to VBN will be equal to VCN. Let me take it to be say VPH. Okay, so if it's an ABC phase sequence, what will you get? If it's ABC phase sequence, for ABC phase sequence, okay, what will be your VAN? Your VAN will be VPH angle 0. Fine. Your VBN will be what? VPH angle minus 120. What will be your VCN? VPH angle minus 240 or plus 120. Okay, so this will be the phase voltages for phase voltages, assuming ABC phase sequence. Okay, now in addition to this thing, you can take the voltage between any two lines. Say for example, between line A and B. Between lines A and B. Okay, this is line A and this is line B. Okay, between lines A and B. So I can write this as VAB. Okay, or between lines B and C. Where is line B? Line B is here, line C is here. Okay, between lines B and C, VBC. Or between line C and A. Between line C and A. That is called line voltage VCA. Okay, since that represents voltages between any two lines, they are called line to line voltages or line voltages. Okay, line to line voltages, line to line, or simply line voltages. Okay, which are the line to line voltages or line voltages here? VAB, VBC, and VCA. Okay, what are the phase voltages? They are VAN, VBN, and VCN. You should not get confused. Okay, so line voltage is something, phase voltage is something else. Okay, so that's what we are going to see today. So let me write here some points. Voltage across each coil is called voltage across each coil or phase. Voltage across each coil or phase is called phase voltage. Phase voltage. Okay. It is also the voltage between. It is also the voltage between. It is also the voltage between each line and neutral. Each line and neutral. And hence also called line to neutral voltage. And hence also called line to neutral voltage. Okay, so what are the phase voltage or line voltage here? VAN, VBN, and VCN. Okay, VAN, VBN, and VCN. Okay, these are the phase voltages or line to neutral voltages. Okay, So since it's a symmetric system, magnitudes are equal. Okay, so can you tell me what will be the phasor sum of VAN and VBN and VCN? What will be the phasor sum? It's a symmetrical system, it's a balanced system, symmetrical system. Okay, how will you find that? You just substitute these things. VPH angle 0 plus VPH angle minus 120 plus VPH angle minus 240. Okay, or if you take VPH common, what will you get? VPH into 1 angle 0 plus 1 angle minus 120 plus 1 angle minus 240. What will you get? It will be equal to 0. Why it is 0? Because it is a balanced, it is a symmetrical system. Okay, in a symmetrical system, in a symmetrical system, these voltages are equal in magnitude. These voltages are equal in magnitude, and further VAN plus VBN plus VCN equal to 0. Okay, that's about the phase voltage. Now let us discuss about line voltage. So what are the line voltages? Line voltages are those voltage between any two lines. Okay, so VAB means what? Voltage between line A and line B. VBC means voltage between line B and line C. Okay, so next is line voltages. Voltage between two lines. Voltage between two lines is called line-to-line voltage. Line-to-line voltage or line voltage. Okay, so what are the line voltages here? The line voltages are VAB, VBC, and VC. Okay, so the line voltages are VAB, VBC, and VC. Okay, VAB, VBC, and VC. Right now, a relationship exists between the line voltage and the phase voltage. Let us see what it is. Okay, relationship between the phase voltage and line voltage in a balanced Y connection. Relationship between phase and line voltages in a balanced three-phase Y connection. In a balanced three-phase star connection. Okay, so let me draw this figure once again here. Okay, this is A, this is B, this is the neutral point. Okay, so these are the lines, line A, line B, lines. Okay, and here is our neutral. This is the neutral. Okay, okay, so VAN is the phase voltage VN, then VBN is the phase voltage, and VCN is the third phase voltage. Okay, so this is VAN, BN, and this is VCN. Okay, these are the phase voltages. Right now, let me mark the line voltage AB. Okay, VAB, then BC. This is BC. So BC. So this is VBC. Okay, and finally VCA. VC. Okay, so what are the phase voltages? Phase voltages are what? VAN, then VBN, and VCN. What are the line voltages? Line voltages are VAB, VBC, and VC. Okay, these are the line voltages. Okay, so these are the respective line voltage and phase voltage. Right now, so these are the phase voltage and line voltages. Right now, you consider this lines A and B. Okay, so our aim is to find the relationship between the phase voltage and the line voltage, right? So VAB, right? So when you say VAB, which is at the lower potential, which is at the higher potential, this is at lower potential, this is at higher potential. Okay, so you are applying KVL to this closed loop. Okay, to the loop that consisting from this thing, phase A and phase B. Okay, so by KVL, what will you get? VAB, it's a positive potential rise, right? VAB means B is at lower potential, A is at higher potential. So this line voltage will be what? VAB. Then as you move, this is plus, this is minus, this is minus, this is plus. Okay, because it's a generator, and we know that current will flow always from the positive polarity to the outside one. Okay, so as you move along this way, this is minus to plus potential rise, VAB, then plus to minus potential drop. So VAB minus VAN. Okay, VAB minus VAN, then minus to plus potential rise plus VBN equal to what? Equal to 0. Okay, KVL, algebraic sum of EMFs in a closed path must be 0. Okay, algebraic sum of EMFs in a closed path must be 0. Right? So if you apply KVL in this loop, you will get VAB minus VAN plus VBN equal to 0. Right? Or that means what is VAB? VAB is nothing but VAN minus VBN. Okay. Now we are considering a balanced three-phase connection. Okay. So since it is balanced, I can write VAN as magnitude is V, VBN magnitude as VPH, and VCN the magnitude as VPH. It's a phase voltage, right? So since it is a balanced supply system, coils are identical. So all the phase voltage magnitudes are one and the same, VPH, right? Now if you take ABC phase sequence, right? The positive phase sequence, ABC phase sequence, and VAN as the reference. Okay, this is my VAN, this is VBN phasor, and this is VCN. Okay, I can write this as angle 0 for ABC phase sequence. Following ABC phase sequence, this will be minus 120, this will be minus 240. Just substitute that here. So what will you get? VPH angle 0 minus VPH angle minus 120. Okay, so you can take VPH outside, you will get VPH into what? 1 angle 0 minus 1 angle minus 120. Okay, so if you do that, you will get a root 3 times VPH angle 30 degree. Okay, so what is VAB? VAB is the line voltage. Okay, so what did you get? Root 3 times VPH angle 30. Similarly, if you apply KVL to this line BC, that loop, okay, by KVL, what would you get? You would get VBC minus VBN plus VCN equal to 0. Are we getting that? Just see VBC, whether B and C is this thing. Okay, so VBC, right? So plus VBC, then minus VBN, right? And plus VCN equal to 0. Okay, or what will be your VBC? VBC will be VBN minus VCN. Okay, what is VBN? VPH angle minus 120. What is VCN? VPH angle minus 240. Okay, so if you do this thing, you will get this as root 3 times VPH angle minus 90. Okay, similarly, if you apply KVL to the other loop, what did you get? VCA minus VCN plus VAN equal to 0, or VCA will be VCN minus VAN. Okay, what is VCN? VPH angle minus 240. What is VAN? VPH angle 0. So what would you get? Root 3 times VPH angle, how much? Minus 120. Okay, sorry, minus 150. Minus 150. Okay, minus 150 or minus 270 you will get. Okay, not minus 270, minus 210 you will get. Okay, minus 210. Minus 210. Right? So what's the meaning of this? It means that the respective line voltages will be leading the respective phase voltage by what? By 30 degree. Okay, and you see what's the line voltage magnitudes? They are all equal. Root 3 VPH, root 3 VPH, and root 3 VPH. Okay, magnitudes are equal and they also differ by 120 degree. Okay, so what's the conclusion? So if you add the line voltages VAB, VBC, and VCA, what you should get? You should get 0 because it's a balanced symmetrical system. Okay, now let us draw the phasor diagram. So suppose okay, so say this is my VAN. Okay, this is VBN and this is VCN. Okay, so we had seen what is VAB. VAB is VAN minus VBN. Okay, VAN minus VBN. So this is my VAN and this is this negative VBN. Okay, so parallelogram law. Okay, so this will be VAB. So you see VAN was at reference angle was 0 degree, right? VAN reference was 0, right? But the respective voltage, line voltage VAB is leading by 30 degree. So this is 30 degree. Okay. Similarly, what is VBC? VBN minus VCN. Parallelogram law, huh? So you will see that your VBC will be something like this. Did I make a mistake? No. VAB. So this should be VBN minus VCN, right? VBN minus VCN. This is VBN. This is minus VCN. Yeah. So this will be again 30 degree. Be leading. Okay. Similarly, what is VCA? VCN minus VAN. VCN minus VAN. So this is our minus VAN. Okay. So this will be somewhere here. VCA. It will be leading VCN by 30. Okay, that is what is shown here. Okay, so this is VAB, then VBC and VC. Okay, so you see the respective angles between the two line voltage will be again 120 degree. Okay, that means line voltages are also symmetric and balanced. Okay, so let us write some points here. Point 1. Line voltages are 120 degree apart. Line voltages are 120 degree apart. Okay, then line voltages are 30 degree ahead. Line voltages lead the respective phase voltages by 30 degree. Okay, Which phase sequence did we assume? We assumed ABC phase sequence. Otherwise, it will be in the opposite way. It will be lagging by 30 degrees. Okay. Then angle between. Okay, that is fine. That's fine. Okay. So line voltages are 120 degree apart, and they lead the respective phase voltages by 30 degrees. Okay. Keep in mind we have assumed anticlockwise rotation or ABC phase sequence. Right. Now, what about the currents? See, so this EMF is being generated, right? When you connect it to a load, current starts flowing. Okay, so this is the phase current. Let me mark this as current IA. So since this phase is joined in series with the line, what happens? This phase current IA will be flowing through the line as line current, or in short, phase current will be same as line current in a star connection. Okay, sorry, see, this is phase, right? This is IA. Okay, so in a star connection, line current and phase current are same. Okay, that's a relationship between line current. So in a star connection, I line is equal to IPH, whereas V line is equal to √3 times VPH in magnitude. Okay, now how will you find the total active power consumed, total three phase power? How will you find? If it was single phase power consumed, three phase power consumed. Okay, how would you find that? 3 into power per phase. Okay, that means 3 into voltage IPH into VPH into IPH into cosine of angle between the two. Okay, cos phi, right? But we know in a star connection, what is V line? V line is √3 times VPH. Okay, or VPH I can write as VL divided by √3, right? And IPH is same as IL, so IL into cos phi. So what will you get? √3 times VL IL cos phi. Okay, this will be the total power consumed in watts, WATTS. Okay, similarly, if you are asked to find the apparent power, the three-phase apparent power, what will you do? Three-phase apparent power. How will you find? 3 into VPH IPH. Okay, again, √3, you will get √3 VL IL. Okay, so this is how voltages and currents are related in a star connection. Okay, now let us take up some examples. Now we'll try some numerical examples, okay, to reinforce what we have learned so far. Q1, question 1. A balanced star connected load, a balanced star connected load of 8 plus J6 ohms, 8 plus J6 ohms per phase is connected to a balanced three-phase 400 volt supply. 400 volt supply. Find the line current. Find the line current. Find the line current, power factor, power, and total volt amperes. Okay, a balanced Y-connected load of 8 plus J6 ohm per phase is connected to a balanced three-phase 400 volt supply. Find the line current, power factor, power, and total volt ampere. I forgot to tell you one thing. When will you say a supply is balanced or symmetrical? Okay, voltage supply. Okay, it is said to be balanced if all the voltages have a magnitude or equal magnitude, VPH, 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 or VL, VL, VL. Okay, and if you're assuming ABC phase sequence, all the angle differences must be 120 degree. Okay, that means any two voltage phase angle difference between any two voltages must be always 120 degree. Okay, so you see VPH, this is a symmetrical or a balanced supply, I can say, because magnitudes VPH, all magnitudes are equal VPH, and there is an angle difference of 120 degree. For example, say, let me write something like this. Say 230 angle 0, 230 angle minus 120, 230 angle minus 240. Is this a balanced supply? Yes, it is. Why? Because the voltage magnitudes are equal and there is a difference of 120-degree phase difference between the voltages. Okay. But suppose this was 240 angle 0, 230 angle minus 120, 230 angle minus 240. Then it would not have been a symmetric or a balanced supply. Okay. Why? Because the first voltage magnitude is 240 volts. Okay. Or suppose it is 230 angle 0, 230 angle say minus 100, 230 angle say minus 240. Is this balanced supply? No. Why? Even though the voltage magnitudes are equal, the phase angle difference is not 120-degree. Okay. So you say a supply, voltage supply is balanced only if the voltage magnitudes are equal and the phase difference between two voltage phases must be always 120-degree. Okay. Similarly, when will you say a load is balanced? A load is said to be balanced if they are equal both in magnitude and angle. That means all the load impedances must be Z angle theta, and Z angle theta, right? If one of the impedances is Z angle minus theta, then it is not a balanced load. Okay, everything must be equal both in magnitude and angle part. Then only you say the load impedances are balanced. Okay. Now, what's the question? A balanced Y-connected load of 8 plus J6 ohm is connected. Okay, so we have a star connection here. Okay, how much is the load? 8 plus J6 ohms. 8 plus J6 ohms. 8 plus J6 ohms. Okay, is connected to a balanced supply. Okay, so here we have a generator which is like this. Okay, say this is A, this is A, this is B, this is B, this is C, and this is C. Okay, is connected to a balanced three-phase 400 volt. What is this 400 volt? Is this line voltage or the phase voltage? 400 volt given is always the line voltage. Okay, so you are given the line voltage magnitude. In a three-phase system, when you mention a voltage, if nothing is specified, then that's to be taken as the line voltage. Okay, so 400 volt is the line-to-line voltage given here, right? Now we know it's star connection. So what will be the phase voltage? Phase voltage will be VL divided by root 3. That means 400 by root 3. Okay. Now we have to assume one of the phase sequences, right? So let us take the positive phase sequence, assuming ABC sequence, phase sequence. Okay, assuming ABC phase sequence, right? So VAN will be what? VPH angle 0. VBN will be what? VPH angle minus 120. And VCN will be what? VPH angle minus 240. Okay, so we know what is 400 by root 3, right? So this will be 400 by root 3 angle 0. This will be 400 by root 3 angle minus 120. This will be 400 by root 3 angle minus 240. Okay, what's the question? Find the line current. Okay, so you know the phase voltages 400 by root 3 angle 0 and so on. Okay, you know the phase impedances 8 plus J6. So how can you find the phase current? Phase voltage divided by phase impedance. Okay, that will give you the phase current. And we know in a star connection, phase current and line current are one and the same. Okay, so phase currents. IAN. What will be that? VAN by ZA or ZAN. You can write because there's a neutral point here. Okay, so what do you get? 400 by root 3 angle 0 divided by 8 plus J6. Okay, what will be IBN? VBN divided by ZBN. 400 by root 3 angle minus 120 divided by 8 plus J6. What will be ICN? For VCN divided by ZCN. That means 400 by root 3 angle minus 240 divided by 8 plus J6. Okay, so your so this magnitudes must be around 23.1 ampere magnitudes only. Okay, so you can find what is the respective angles also from this. Okay. So this will be same as the line current. So IL equal to IPH, that will be equal to 23.1 amperes. Okay. So if you do this calculation, you will get how much should be the angle. Must be 23.1 angle something. 23.1 angle something. This will be 23.1 angle something. Right. Keep in mind, since it is balanced, the angle difference between currents will also be 120 degrees. Okay, you can verify that, cross verify that. Okay. Now, what next? You are asked to find power factor. What is power factor? Power factor is the cosine of angle between the voltage phasor and current phasor. Is it not? Phi, cos phi will give you power factor. So IAN we know. You will get IAN in phasor form. 23.1 angle, some angle you will get. Say let that angle be phi, right? What's VN angle? It is 0 degree, right? So cosine of phi, that will give you the angle power factor, this thing. Okay. That will give you the power factor. And that turns out to be around 0.8. You should get a power factor of around 36, power factor angle of 36.86. So you will get approximately as 0.8 lag. Okay. Then what next? You are asked to find power. How will you find power? Power is nothing but root 3 VL IL cos phi. Okay. VL value we know 400. IL value we know. We had found it 23.1 into cos phi is 0.8. So that must be around close to 12,800 watts. Okay. What next? We are asked to find the total volt ampere. How will you find the total volt ampere? Root 3 VLIL. Is it not? Total volt ampere will be what? Root 3 VLIL. Okay, just substitute. VL value we know, IL value we found. That will be around 16,000 volt ampere. Okay. Let us try another question. Question 2. Phase voltages of a star connected alternator are phase voltages of a star connected alternator are 231, sorry, VAN equal to 231 angle 0 volt, VBN equals 231 angle minus 120 volt, and VCN equals 231 angle plus 120 volt. What is the phase sequence? What is the phase sequence? Okay, compute the line voltages. Compute the line voltages. Compute the line voltages. Okay, so you are given what VN is 231 angle 0, VBN 231 angle minus 120, and VCN 231 angle plus 120. See, moving anti-clockwise direction is positive and clockwise direction is negative. Okay, so plus 120 is same as minus 240. So I can write this as 231 angle minus 240. So now you tell me what is the phase sequence? It is ABC phase sequence or RYP or positive phase sequence. Okay, that's clear. Now you have to compute the line voltage, right? So what will be VAB? VAB will be VAN minus VBN. Okay, so here the magnitude will come to be around, or simply you can find. We know what is VL. VL is root 3 times VPH, right? VPH magnitude is given 231, so that will be around close to 400 volt. Okay, close to 400 volt. So if you are writing it in phasor form, can you tell me what's VAB? It will be 400 angle plus 30. Okay, because we are seeing the line voltages will be leading the respective phase voltage by 30 degree. Okay, so since VAN angle 0 degree, VAB angle has to be plus 30. That 30 you have to add from your hand. Okay, plus 30. Then what will be VBC? VBC will be what? 400 angle minus 90. And what will be VCA? It will be 400 angle plus. What will be the angle? Plus 150 plus 150. Okay, so these will be the line voltages. One more question. 3 equal star connected inductors take Q3. Question 3. 3 equal star connected inductors. Star connected inductors take 8 kilowatt at a power factor of 0.8. At a power factor of 0.8. When connected across a 460 volt 3 wire supply. Find the circuit constants of the load per phase. Find the circuit constants of the load. Find the circuit constants of the load per phase. Okay. 3 equal Y connected inductors. Okay. So the inductors are, or the rather impedances are Y connected. Okay. Take 8 kilowatt at a power factor of 0.8. Whenever you say power factor, if it is other than UPF, it must be always accompanied by lead or lag. Okay, then only power factor has meaning, right? But here the question is, it is clearly given. 3 equal Y connected inductors means what? Power factor is 0.8 lagging. Okay, so power factor cos phi is 0.8 lagging. Now, takes 8 kilowatt. Okay, 3 equal Y connected inductors take 8 kilowatt when connected across a 3-phase supply. Means what? It is a 3-phase power. So root 3 VL IL cos phi is given as how much? 8,000 watts. Okay, when connected across a 460 volt. What is 460 volt? It is the line voltage. Okay, so you are given the line voltage magnitude as 460 volt. So assuming ABC phase sequence. Okay, ABC sequence. Okay, or I will come to that later, right? So from here you can find what's your IL. What will be your IL? 8,000 divided by root 3 into 460 into 0.8. Okay, so your IL will turn out to be around 12.55 ampere, right? Your line current will turn out to be 12.55 ampere. We know that in a star connection, I line and IPH are one and the same. So that means your IPH is nothing but 12.55 ampere. Okay. Now, what will be IA, IB, and IC? Any idea in phasor form what will be there? IA magnitudes will be equal 12.55, 12.55, 12.55. What will be the respective angles? Any idea? That is why we are going to power factor angle 0.8 lagging. So IA will be 12.55 angle minus 36.86. What will be IB? What will be IB? IB will be 12.55 angle minus 156.86. And what will be IC? 12.55 angle minus 276.86. Okay. See, don't get confused. Okay, it's easy. These are your phase voltages VAN, VBN, VCN. Okay, 3 equal Y connected inductors. Okay, so that means this must be your IA, this must be your IB, and this must be your IC. Keep in mind, this is the positive phase sequence. Okay, if you take a point here first, reference point X, first VN will come, then after 36.86, IA will come. Okay, then VBN will come, then after 36.86, IB will come. Then VCN will touch the point, and after 36.86 degree, IC will touch. That's the meaning. Okay, so these are the respective currents in phasor form. Okay, now what next? So we know the voltage magnitude, the line voltage magnitude, and the line currents also, or the phase currents. Okay, so what will be the per phase? What, assuming ABC phase sequence? what will be the phase voltages? How will you find the phase voltage? You know the line voltage value. What will be phase voltage? Phase voltage will be VL divided by root 3. So you will get 460 by root 3 angle 0. Okay. What will be your VBN? VBN will be 460 by root 3 angle minus 120. And phase voltage BCN will be 460 by root 3 angle minus 240. Okay. So from here you will get what is the phase voltage magnitude. What is that? VL divided by root 3. That will be around 265 volt. 265 volt close to. Okay. So now you know the phase voltage, you know the phase current value, magnitude. Okay. So you can find the impedance, Z per phase. What will be that? VPH divided by IPH. How much will you get? You should get a value of around 21.1 ohms. Okay. 21.1 ohms. So if you remember the impedance triangle, this is Z, this is R, this is JX. Okay. And this is the power factor angle phi. So Z we know, Z magnitude we know, 21.1 ohm. Phi also we know, it is 36.86. So you can find what is R, Z into cos phi. And that turns out to be around 16.9 ohms. Okay. And what will be X? It will be Z sin phi. How much is that? That will be around 12.66 ohms. That is one way. Or you simply take the ratio of phasor voltage to phasor current. Okay. So ZA will be what? VAN divided by IA. Okay. So you will get something. What is that value? Do that calculation. You will get say something. Let me assume you are getting some value Z angle theta. Okay. Convert this into rectangular coordinates. You will get the resistance, you will get the reactance. So your R must be around 16.9 plus J 12.66. Okay. So in this way, you can identify what are the circuit constants. Okay. So we'll stop here, and the next class we will take up a delta configuration. Okay. Thank you.